Hey guys, so this week we're doing more reactions, more collision theory, etc. So let's jump right into it. So number one, according to collision theory, what are the requirements for a reaction to occur? So we have three. There we go. We have three requirements. Our first requirement, called collision theory, our first requirement is that the particles collide. Our second requirement, the particles, when they collide, they have to collide with the proper orientation for the reaction to occur. And our third requirement is when the particles collide, that they collide with sufficient energy. So those are the three things needed for a reaction to occur. Which of the following conditions will affect the rate of reaction? Select all that apply. So if you have a decrease in temperature, you're going to have a decrease in the movement of the particles, right? Which is going to mean fewer collisions. And you're also going to have a decrease in the energy of the particles. So when you have fewer particles moving, fewer of them are going to collide, so it's less likely that they'll both collide in the proper orientation and with sufficient energy. And if your energy is decreased, then you have like double the sufficient energy being decreased. So that means that this will cause the rate of reaction to decrease. If you have a higher volume of concentration, well, you still have the same. Basically, when you look at those, like kind of how the rate of reaction, that's going to be dependent on the concentration of the particles, not necessarily the volume of the particles. And since the energy is staying the same, that's not really going to affect anything. So the volume of the concentration will not affect the rate of a reaction. A higher concentration of reactants, well, that's going to mean you have more particles. And if you have more particles, it's more likely that they'll collide in the proper orientation and with sufficient energy. So that's going to increase your rate of reaction. The presence of a catalyst. Remember, a catalyst is kind of like you're decreasing the amount of energy, the amount of activation energy needed, and you're also increasing the likelihood of having them collide in a proper orientation. It's almost like if you have a catalyst kind of provides a template for the reactants to collide, almost like a magnet or something. So not only are you decreasing the amount of energy needed, so basically the amount of energy, sufficient energy, is going to go up, if that makes sense. Since the amount of energy you need is, the likelihood that it has sufficient energy is increasing, The likelihood it's going to have sufficient energy is increasing because the amount of activation energy needed is going down. And then also the likelihood of proper orientation is going up because, again, a catalyst kind of acts like a template for those reactants to collide. That's going to increase your rate of reaction. And a granular size of reactants, so more surface area, that means that there are more particles available to collide, which again will mean greater likelihood that they collide with the proper orientation and sufficient energy. So again, that will increase. So all of these, except for the higher volume of reactants, is going to affect the rate of reaction. Number 3, for the decomposition of hydrogen peroxide in the presence of a catalyst. Okay, so basically it says that if there's a catalyst present, yes to a catalyst present, then we'll need greater than 56 kilojoules per mole of energy for the reaction to occur. And if there's not a catalyst present, then we are going to need more than 75 kilojoules per mole for a reaction to occur. So now we're going to, now we want to predict whether or not the reaction will occur. So I'm going to add another column actually. Okay. Just to kind of, okay. So, I'm going to add this new column, and I'm going to call it kilojoules per mole of energy. And what I'm going to do is I'm going to divide the amount of energy added divided by the number of moles. So 65 kilojoules divided by 1 mole is just 65 kilojoules. 65 divided by 1 mole, again 65. 155 divided by 2, that's going to be, let's see, 155 divided by 2 is going to be 77.5, I believe, kilojoules per mole. And 24 divided by 0.5, that's 24 times 1/2. 24 times divided by 1/2 is equal to 24 times 2 is going to be 48. So now we're going to go through these and see whether a reaction would occur. So there's no catalyst present, so that means there needs to be at least 75 kilojoules per mole of energy. We only have 65, so a reaction isn't going to occur there. So now we do have a catalyst present, and we still have 65 kilojoules per mole of energy added, and we need at least 56 moles. So yes, a reaction will occur there. Here, we don't have a catalyst present, but we have more than 75 kilojoules per mole, so a reaction will also occur here. And here we do have a catalyst present, but we need 56 kilojoules per mole and we only have 48, so a reaction will not occur there. Okay. In the diagram below, label the reactant, product, transition state, activation energy, and the enthalpy of the reaction. Would you expect the enthalpy to be positive or negative, and why? Okay, so let's start with labeling all this stuff. So a reactant, remember, that's your starting material. Your product is what you end with. The transition state is this high energy intermediate. It's kind of unstable. Remember, it has a really high energy, so that makes it kind of unstable. It's kind of at the tip of this peak, and going either direction is going to decrease the amount of energy and make it more stable. And then the activation energy is the amount of energy it takes to get up to that transition state. And the enthalpy of the reaction, remember, is how much it takes to go from the reactants to the products. And so this is the enthalpy. And in this case, it's going to be negative because the energy of the reactants is greater than the energy of the products. Number 5, we're labeling the energy diagram. So let's start off with, we have our coordinates here, A and B. And A, remember, on this energy diagram is going to be energy. Because basically this is showing, okay, you start with this much energy, as the reaction progresses, the energy increases, and it's going to decrease until we get to the energy of the products. And on our B, basically what's happening is we're looking at how the reaction is progressing kind of over time, I guess. So that's we're gonna call that the reaction coordinate. And that's B. C, so it looks like we have C and D are both some sort of activation energy. And one of those is going to be the activation energy in the forward direction, and the other one is going to be the activation energy in the reverse direction. So in the forward direction, if we're going from products to reactants, remember the activation energy is the amount of energy to get from the reactants to the transition state. And so when you have an exothermic reaction like this, your activation energy is going to be actually always, so basically the C is going to be the forward activation energy, because that's where the reactants start. And then if you do it the reverse way, so it's an endothermic reaction, you're going to have, it goes all the way up. So you need to get from H to F. So it's going to take all that energy to reach the transition state. So that is going to be D in the reverse direction. E, let's see, where's E? So E here, again, either whether you're going in the forward or the reverse direction, that's going to be, remember, you have the activation energy, and you also have the change in energy between the reactants and products, and that's the enthalpy. So that's E. I'm going to write that up here. So the change in energy between the reactants and the products. And remember, so even in the forward or reverse direction, it's always going to be, I'm going to put like an absolute value. So basically, it's always going to be that same amount, whether it's forward or reverse. If it's forward, it's going to be negative, right? Because the products have less energy than the reactants, so energy is being released. I'm just going to erase that. That's wrong. If you want the enthalpy, it's going to be the energy of the products minus the energy of the reactants. But yeah, so it's easier to look at the graph. So sorry I got that wrong, but basically the enthalpy change is always going to be either positive or negative. It's positive when you go in this direction, it's positive. When you go in this direction, it's negative. EF, we already talked about this. This is the transition state. Let's see. So the transition state, again, is that high energy intermediate state. G, again, those are what we're starting with, so those are our reactants. Reactants. And then H, our last one, those are our products, because that's what we end up with. Okay, how much time do I have? Okay, I'm going to stop here and pick this back up in the next video.